Stop. Look at the space between your eyes and the screen. It looks empty, right? If you're old enough to remember the static on an old television, that snow, that chaotic buzzing hiss between channels, you've seen it. Roughly 1% of that dancing static wasn't caused by the TV. It wasn't caused by radio interference. And it wasn't a glitch. That 1% was light. But not just any light. That static was a photon that started its journey 13.8 billion years ago. It has been traveling in a straight line, dodging galaxies, weaving through nebulas, stretching across the fabric of reality itself, just to end its life by hitting the antenna of your TV. You were watching the Big Bang, literally. But here is the part that keeps me up at night. That light? It's not just noise. It's a photograph. It's a message carrying a specific image of the universe when it was just a baby. And if you know how to develop that film, the picture it shows us is terrifying. It doesn't just tell us how we started, it tells us exactly how we are going to end. Let me show you. We always say light is the fastest thing in the universe, 300,000 kilometers per second, the universal speed limit. If I turn on a flashlight, the beam hits the wall instantly. Nothing can stop it. Wrong. That rule only works if space is empty. But immediately after the Big Bang, space was the furthest thing from empty. Here is the part your intuition struggles with. For the first 380,000 years of existence, the universe was a prison. Light couldn't travel. It couldn't carry a message. It couldn't show you a picture. Why? Because it was too hot. We're talking billions of degrees. It was so hot that atoms, the building blocks of everything you see right now, literally could not exist. Think about a standard atom. You have the heavy nucleus in the middle and the tiny electrons orbiting on the outside, right? Like a calm little solar system. But in the baby universe, the heat was so intense that it ripped those electrons off. It smashed the solar systems apart. The electrons were running wild, roaming free in a chaotic, dense soup of plasma. And here is the problem. Free electrons are the sworn enemy of light. Close your eyes and imagine this. Imagine you are trying to run in a perfectly straight line through a crowded nightclub where everyone is fighting. You take one step, bam, you hit a shoulder. You bounce off, turn left, bam, you hit an elbow. You aren't moving forward, you are bouncing, you are ricocheting, you are trapped in a pinball machine. That was the life of a photon in the early universe. A particle of light would try to move, and instantly it would smash into a loose electron. It would scatter. Then it would smash into another one. Light couldn't travel more than a microscopic distance before being redirected. So, if you could teleport back to year 100,000 after the Big Bang, what would you see? Nothing. You wouldn't see stars. You wouldn't see black space. You would be inside a glowing, thick, blinding fog. The universe was opaque, like milk. Light was there, it was everywhere, but it was locked in a cage made of electricity. It was holding its breath, waiting for a chance to escape. For 380,000 years, the universe was blind. It kept its secrets hidden inside that fog. But then, the temperature dropped, just a little bit. And that cooling effect triggered the single most important event in the history of physics. The cage broke. So, how did the light escape? The universe had been expanding for 380,000 years, and as things expand, they cool down. It's simple thermodynamics. Think of a can of hairspray. When you spray it, the can gets cold in your hand, right? The gas inside expands, and the temperature drops. The universe is just the biggest can of hairspray in existence. For nearly 400,000 years, the temperature was stuck above 3,000 Kelvin. That is roughly the temperature of the surface of a red dwarf star. The entire universe was as hot as the surface of a star. But then it crossed a threshold. It cooled just enough, below 3,000 Kelvin. And suddenly, the magic happened. The chaos stopped. The wild, smashing electrons that were blocking the light, they slowed down. They got tired. And the protons, those heavy nuclei floating around, finally caught them. Snap! An electron got captured by a proton. Snap! Another one. Snap! Hydrogen atoms formed. Neutral atoms. This has a fancy name, recombination. But forget the name. Here is what matters. A neutral atom is incredible at doing one thing, ignoring light. Remember the crowded nightclub? The fighting people? Imagine everyone suddenly sat down at the tables. The dance floor clears. The path opens up. The fog didn't just fade away slowly, it vanished. Suddenly, those photons, the light that had been bouncing around like pinballs for 380,000 years, had a straight path. They looked ahead, and the road was clear. So they ran. Every single photon in the universe took off in a straight line, in whatever random direction it was facing at that exact second. And because nothing was there to stop them anymore, they never stopped running. This moment is called the surface of last scattering. Why last scattering? Because it was the last time light hit something and bounced off. It was the last time the light touched matter. From that moment until now, 13.8 billion years later, that light has been flying through the void, untouched. Wait, think about what this implies. When you take a picture with a camera, what are you doing? You are capturing light that bounced off an object and traveled to your lens. This moment, 380,000 years after the Big Bang, was the flash of the universal camera. The light that escaped carried a pattern. It carried an image of the glowing gas clouds it left behind. It took a snapshot of the universe, exactly as it looked at the moment the fog lifted. That light is still here. It is flying through this room right now. It is passing through your body. If you could see it, the entire sky would be glowing, day and night. So here is the question that should be bothering you. If the whole universe was glowing as hot as a star when this light was released, why is the night sky black? Why don't we see a blinding white wall of fire every time we look up? The answer is terrifying, because it means the universe is doing something to the light. It is torturing it. You see darkness when you look up at night. That's because your eyes are weak. Our eyes are biological instruments tuned to see a tiny, pathetic slice of reality. We call it visible light. It's the rainbow. Red, orange, yellow, green, blue, indigo, violet. That's it. That's the whole show for us. But light is so much more than that. It's a wave. And like any wave, in the ocean or on a guitar string, it can be stretched. When that light first escaped the fog 380,000 years after the Big Bang, it was hot. It was energetic. It was glowing orange-white. It was visible. If you had been there, you would have been blinded by it. So where did it go? It didn't go anywhere. The light is still here. But the space it travels through has changed. This is the part that breaks your brain. Space isn't just a stage where things happen. Space is a thing itself. It can bend, it can twist, and most importantly, it can expand. Since the moment that light started traveling, the universe has been getting bigger, a lot bigger. Imagine drawing a squiggly wave on a balloon with a marker. Now blow up the balloon. What happens to the wave? It stretches out. The peaks get farther apart. The wave gets longer. That is exactly what happened to the light from the Big Bang. As the universe expanded over 13.8 billion years, it grabbed that light by the neck and stretched it. It pulled it like taffy. And when you stretch a light wave, you change its color. It started as visible orange light. As space expanded, the wave got longer and turned red. That's called redshift. But the universe kept expanding, so the light kept stretching. It stretched past red. It went into the infrared, the heat you feel from a fire but can't see. It kept going. The universe got bigger and bigger. The wave got longer and longer. Eventually, it stretched so much that it fell off the edge of the rainbow entirely. It turned into microwaves. Microwaves. Yes, the same waves that heat up your leftover pizza. That blinding wall of fire from the beginning of time is now a cold, faint hum of microwave radiation. It is filling every cubic centimeter of the universe. If you had microwave vision, if your eyes could see radio waves instead of light, the night sky wouldn't be dark at all. It would be glowing everywhere, in every direction, with a uniform brightness. You would look up and see the afterglow of the Big Bang directly. This is what we call the cosmic microwave background, or the CMB. It is the oldest light in the universe. It is a fossil. And for decades, nobody knew it was there. It was hiding in plain sight. We were swimming in an ocean of ancient light, completely oblivious, until two guys in New Jersey stumbled upon it by accident, and they thought it was pigeon poop. I'm not joking. Let's go back to the 1960s, specifically to a hill in New Jersey, Homedale. There were two young radio astronomers there, Arno Penzias and Robert Wilson. They weren't trying to solve the mysteries of the universe. They weren't looking for the Big Bang. They were working for Bell Labs. Their job was practical. They were testing a giant, weird-looking antenna, basically a massive 20-foot-long horn, to bounce radio signals off a giant balloon in space. It was called the Homedale Horn Antenna. Their goal was simple: point the antenna at the sky, listen to the quietest parts of the galaxy, and map the radio waves coming from the Milky Way. But they had a problem. Every time they pointed the antenna at empty space, they heard a noise. A persistent, annoying hiss, like static. Sssss. They checked everything. Was it interference from New York City? No. Was it a military radar? No. Was it coming from the sun? No. Here is the weird part. It didn't matter where they pointed the antenna. Pointed at the horizon? Sssss. Pointed straight up? Sssss. Day? Sssss. Night? Sssss. The noise was coming from everywhere at once. It was uniform. It was driving them crazy. They assumed their equipment was broken, so they climbed inside the giant horn to inspect it. And what did they find? Pigeons. A pair of pigeons had been nesting inside the antenna, and as pigeons do, they had left a white dielectric material all over the inside. That is the polite scientific term for bird poop. Penzias and Wilson thought, aha, the warm poop is radiating heat, and that's causing the static. So they scrubbed the antenna clean. They evicted the pigeons. Sadly, the pigeons kept coming back, so they had to be permanently removed. They cleaned every inch of that horn until it was spotless. They turned it back on. They pointed it at the darkest, coldest part of the sky. Shh! The noise was still there. They were baffled. They had just discovered a signal that was coming from every direction in the universe with equal intensity. Meanwhile, just 30 miles away at Princeton University, a team of theoretical physicists led by Robert Dicke was frantically trying to calculate something. Dicke had a theory. If the Big Bang happened, there should be leftover radiation. He was literally designing an experiment to find it. Then he got a phone call. It was Penzias. Hey, we have this annoying noise we can't get rid of. Dicke hung up the phone, turned to his team, and said the famous words, "Boys, we've been scooped." Penzias and Wilson had stumbled upon the afterglow of creation, the oldest light in the universe, the echo of the Big Bang itself, and they won the Nobel Prize for it. All because they cleaned up some pigeon poop. But the real shock wasn't that the glow existed, it was that the glow was wrong. So the afterglow was found. The universe has a background noise. It's everywhere. But here is the problem. It was too perfect. When Penzias and Wilson measured that hiss, it was remarkably uniform. The temperature of this glow was almost exactly 2.725 Kelvin, everywhere, in every direction. Let me put this in perspective. Imagine you are standing in a blizzard. The snowflakes are falling all around you. If you measure the temperature of the air, it varies. Maybe it's warmer near a building, maybe colder in the wind. But imagine if you measured the temperature in a blizzard and every single cubic inch of air was exactly the same temperature, down to the millionth of a degree. That would be impossible. It would imply that the blizzard was artificial. Or it would imply that the blizzard started from a single, perfectly smooth, perfectly uniform event. For decades, this perfection bothered cosmologists. Why? Because if the early universe was perfectly smooth, if the gas was distributed perfectly evenly, then gravity would have nothing to do. Gravity needs lumps. It needs clumps of matter to pull on. If the gas was perfectly spread out, gravity would pull equally in all directions. Nothing would ever collapse. Nothing would ever form. No stars, no galaxies, no planets, no you. The universe would just be a cold, dark, expanding soup of gas forever. So the Big Bang Theory had a major flaw. It predicted a smooth universe, but we look around and see a clumpy universe. We see galaxies. We see clusters of galaxies. We see huge voids of empty space. Something must have broken the smoothness. Something must have disturbed the perfect soup. We needed to find ripples, tiny imperfections. So we built a satellite, COBE, the Cosmic Background Explorer. We launched it in 1989. Its job was to map the entire sky in microwave light, but with way more precision than Penzias and Wilson. For years, it stared at the darkness. And then, in 1992, the data came back. It was a map of the entire universe when it was 380,000 years old. And it wasn't smooth. It was speckled. There were tiny microscopic variations in temperature. Some spots were slightly hotter, red. Some were slightly colder, blue. How slight? We are talking about differences of 1 part in 100,000. That is like looking at a perfectly smooth billiard ball and noticing a bump the size of a bacteria. These tiny ripples, these anisotropies, were the seeds of everything. The hot spots were slightly denser regions where matter had clumped together. The cold spots were slightly emptier regions. Gravity took those tiny imperceptible clumps and magnified them over billions of years. The dense spots pulled in more matter. They grew heavier. They pulled in even more matter. Eventually they collapsed into stars and galaxies and clusters of galaxies. The structure of the entire universe today, the cosmic web itself, was born from those tiny ripples in the baby picture. If the universe had been truly perfect, we wouldn't exist. We are literally the result of a cosmic imperfection. We are the debris from a tiny wobble in the early universe. But here is the catch. Where did the wobble come from? What caused the ripples in the first place? The ripples are the most beautiful, most important thing in physics. They are the blueprint of everything. The universe is literally written in code. But here is where things get weird. The map is too good. When you look at the CMB, that microwave background radiation, it has a very specific pattern. The ripples are all about the same size. They are distributed randomly, but with a certain graininess. It looks like static on a TV screen. But imagine you took a snapshot of the ocean during a storm. The waves would be all different sizes. Big ones, small ones, choppy ones. The universe wasn't like that. The ripples were coherent. It was almost as if something had synchronized them across the entire sky. Think about 2 cups of coffee sitting on opposite sides of a football stadium. If you measure the temperature of both cups, and they are exactly the same down to the millionth of a degree, that is weird. Unless they were once in the same pot. Unless they were once touching. But in the standard Big Bang model, the universe expanded too fast for light to travel between opposite sides of the sky. One side of the universe shouldn't know the other side exists. They shouldn't have the same temperature. They shouldn't have synchronized ripples. This is the horizon problem. So how did the universe get so smooth? How did it coordinate its temperature across billions of light years in a fraction of a second? There is only one explanation that fits, and it is terrifying. Inflation. The idea is simple but insane. Before the Big Bang was even a tiny fireball, the universe went through a period of exponential expansion. It didn't just expand, it exploded outward faster than the speed of light. I'm talking about doubling in size every trillionth of a second. In a fraction of a second, a patch of space the size of a proton blew up to become the size of a grapefruit, and then it kept going. It became the size of the observable universe. This rapid stretching smoothed out all the wrinkles. It made the universe flat. It made the temperature uniform everywhere. And those tiny quantum fluctuations, those random jitters in the fabric of space-time that happen on the subatomic scale, inflation stretched them out. It magnified them from the quantum world to the cosmic scale. Those microscopic jitters became the giant ripples in the CMB. They became the seeds of galaxies. So when you look at that map of the early universe, you aren't just seeing 380,000 years after the Big Bang. You are seeing the fingerprints of a process that happened in the first fraction of a second of time itself. You are seeing quantum mechanics painted across the sky. But here is the final twist. The map doesn't just show us the beginning, it shows us the end. If you look at the cosmic microwave background map closely enough, it whispers something terrifying. It tells us how much matter there is in the universe. It tells us how fast space is expanding. It tells us the shape of space itself. And it gives us a prediction. There are three ways the universe can end. The big crunch, gravity wins. The expansion stops, reverses, and everything collapses back into a singularity. Fire, the big rip, dark energy wins. The expansion accelerates so fast that galaxies, stars, and even atoms are torn apart. Chaos. The big freeze, a perfect balance. The universe expands forever, but slowly cools down until every star burns out and time loses meaning. Silence. For decades, we didn't know which one it would be. We were guessing, but the CMB map gave us the numbers. The ripples told us the density of the universe is almost exactly the critical density. That means the universe is flat, spatially flat. And a flat universe doesn't crunch. It doesn't rip, probably. It freezes. The light from the Big Bang is telling us that the universe will expand forever. It will get colder and colder. The stars will die one by one. The black holes will evaporate. And eventually, the universe will be nothing but a cold, dark, empty void with a temperature of absolute zero. The light that started it all, the light we are looking at right now, is slowly fading away. In a few trillion years, the expansion of space will stretch the CMB waves so much that they will become undetectable. Future civilizations won't see the afterglow. They won't know about the Big Bang. They will look up at a perfectly black sky and think the universe has always been this way, static and eternal. We are living in the only time in history where we can see the truth. We started this journey with a piece of static on an old TV, a tiny bit of noise, a ghost in the machine. But now you know what that ghost is. It's the voice of the universe, shouting across 13.8 billion years of history. It's a photograph of the moment the lights turned on. It's a map of the tiny imperfections that created you. And it's a prophecy of how everything will end. Think about the odds. The universe had to cool down at exactly the right speed. The electrons had to combine with protons at exactly the right moment. The light had to escape. The space had to stretch. The ripples had to form galaxies. And then, billions of years later, two guys in New Jersey had to clean some pigeon poop out of a horn antenna. If any of those things didn't happen, we wouldn't know where we came from. We wouldn't know where we are going. We are the only creatures in existence who can look back at the beginning of time. We are the universe's way of looking at its own baby picture. So the next time you see static on a screen, or look up at the dark night sky, remember this: you aren't looking at nothing, you are looking at everything.